Okay, welcome to the video for section 2.4 of the Rogowski AP Calc textbook. This video is going to talk all about limits and the concept of continuity. Okay, my goal in this video, because we have the extended break for the World Meeting of Families, is to kind of give you a decent amount of the notes that you would have gotten had we been in school Wednesday, Thursday, and Friday of this week on continuity. Give you the opportunity to do some practice problems both with me, and then I have a homework assignment for you to try on your own using some of these concepts of continuity. And then that way when we return after the World Meeting of Families and the papal visit this following Monday, we can kind of fill in any gaps you might have about continuity from watching this video, and then not lose too much ground as we keep going in our story of limits and calculus. Okay, as always, pause the video, rewind the video at any point if anything I say is unclear, or if you need to, scribble some notes down in your notebook. Make notes of any questions you might have, because I will take any questions that you have. You can either email me during the break, or you can talk to me about it in class on Monday. I want to keep going with the curriculum. I don't want to use these couple days as kind of a break, if you will, in the action. So that's why I'm assigning this video. Okay, so I appreciate you watching this and really interacting with it over the next few days. So let's start with an intuitive definition, okay, of this word continuity. So I went online and I looked up in the dictionary what the word continuity means just in general. So it says it means forming an unbroken whole or without interruption. So if we take that dictionary definition of what just the word continuity means and we apply it to something mathematical, one can surmise that for a function to be continuous, that must mean you have to draw its graph without any breaks. Okay, and that's kind of the way I learned it when I first was a math student doing advanced math, pre-calc and calc in high school. My teachers used to say a continuous function is one that you can graph without picking up your pencil off the paper. And in some respects, and in some questions, if I give you a bunch of graphs and I ask you which one is the continuous one and which one is not, that intuition works. But on the AP exam, especially with the free response questions, they're very known for throwing in problems where you have to prove that something's continuous or make something continuous. So we need a little bit more of a rigorous mathematical definition. So that's going to be coming up in a few slides. But first, let's apply the intuition. I have two pictures here. I took them from some of the diagrams from the Rogowski textbook. The left graph is continuous, particularly at the point x equals c that's highlighted right here, because as you pass c on the x-axis, you don't lift up your pencil, right? We just kind of go right through c. Now, on the graph of this function g on the right, g is what we would call discontinuous at x equals c. Because you can draw this first piece without picking up your pen, but then when you get to x equals c, you draw this closed dot, and then you have to jump up a couple units, have an open hole, and then continue drawing g of x. This area that I circle here is going to be a point of discontinuity, and there are a couple different types of points of discontinuity, which we will get into later on in this video. But for right now, just realize that this is discontinuous. Okay, so let's talk about this rigorous mathematical definition. And here it is. This might be a good point to pause the video, get this in your notebook, and then I can talk about it a little bit. So what it means to be continuous at a point, and we'll call that point x equals c. Three conditions must all hold, and here they are. Okay, the function has to be defined at c, so f of c must exist and be a value. The limit as x approaches c of the function must exist. And remember, we talked about in the last section, what that means is as you approach c from the left and you approach c from the right, you get closer and closer to the same value, right? We talked about this two-sided limit issue. When we say limit as x approaches c, we're talking about from both sides. It's a two-sided limit. So not only must the function be defined at the point c, and not only must the limit exist at the point c, but those two things must be the same value. Your limit as x approaches c of f of x equals f of c. Now, I think in the Rogowski textbook they only mention this condition, but I like to break it down into all three of these parts because when you talk about or when you prove that something's discontinuous, it's usually because one of these three things is broken down somewhere. And we'll talk about those different things. Okay, so if we go back to that picture, now it makes sense why the left graph is continuous and the right graph is not continuous. See, so we'll start with the discontinuous example. If you look at C, does f of c exist? Yes, it's right here. But the limit as x approaches c from the left does not equal the limit as x approaches c from the right. Because as we go to the left, we get closer and closer to the dot. But as we come in from the right, we get closer and closer to the hole. So as a result, the limit as x approaches c of f of x, the c should actually be down here, does not exist. So as a result, we've broken one of those three conditions, so we have a discontinuity at c. Okay? Here's some basic continuous functions. And again, I'm not going to go through the three conditions, but I think you can see on your own why these are continuous, not just intuitively, but with limits. So the constant function is going to be continuous at c, because as we talked about with limit laws, we already know the limit as x approaches c of a constant has to be the constant. And we also know that f of c has to equal k because it's a constant function. Whatever we put in as our independent variable is kind of irrelevant. The dependent will always be k. Okay? A linear function, g of x equals k, will also be continuous because the limit as x approaches c of f of x, well, in this case it's g of x, is just going to be c, right there, which is another one of our limit laws. And f of c is going to equal c because, again, it's linear. There's your point. So the limit does equal the function value. Yes, it's continuous. Now I want to go through and talk about some of the different types of discontinuities and where those three conditions can break down. The first type we've already sort of talked about. Okay? It's a removable discontinuity. So this is a situation where we do have a limit at the point x equals c, but it's not the same value as f of c. We call that a removable discontinuity. These are those holes we've talked about. These are those situations where you have a rational function and you can cancel out common factors of the top polynomial and the bottom polynomial. That's a removable discontinuity. Your book refers to these as what they call a mild discontinuity. And the reason why it's mild is because it's very easy to make it continuous. Just redefine f of c. So for instance, here's what they mean by that. This is a picture I got from your book. So graph A down here has a removable discontinuity at x equals 2 because as we take the limit of either side of the function, we get closer to 5. However, f of 2 equals 10. So we would say that the limit as x approaches 2 of f of x does not equal f of 2. Therefore, it's not continuous at 2. To fix that, you just take the dot and fill in the hole. You can redefine f of c to say, okay, well, let's make f of 2 equal 5. Now f is continuous at x equals 2. This will happen sometimes with piecewise functions. You know, this might have been a piecewise function for everything except x equals 2. So just change it and say, well, when x equals 2, have it be a part of the function. And you're all good to go. Filling in the hole. Okay? A couple other examples of discontinuity. So a jump discontinuity. This is kind of like that piecewise that we saw one day in class. Remember the absolute value of x over x? And we had this graph where we had it going one way with the hole at +1, and it was going the other way with the hole at -1. The reason why this is a jump, because we have one-sided limits, but they're not equal. Because remember, if we make our c 0, as we talked about in class in section 2.2, I believe it was, the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right of f of x, because this one was -1 and that one was +1. So for that reason, we have something that's discontinuous at 0. This is a little bit of a harder discontinuity to fix, because you really can't redefine this function to make it continuous, right? These are basically those piecewise functions that sometimes just don't line up at the endpoints, like you see right here, okay? Now, while we talked about continuity and we talked about two-sided continuity, your book also mentions something called one-sided continuity. And that just means if either the limit from the left or the limit from the right equals the function value, you can call the function either left or right continuous at x equals c. Okay, and I'll show you some pictures of that in the next slide. There are some exercises in the book where they'll talk about left continuous or right continuous. They're just asking you to apply this definition. At what values does the left-hand limit equal the function value, or the right-hand limit at a point equal the function value at that same point? Okay, and here's some pictures of what that means. Try exercises 2-4 on page 88. Pause the video and give it a try. This is the figure that's in your book that uses that. Once you pick up the video, at this point, I will go over those answers. Okay, so if we discuss the problems from 2-4, hopefully you gave it a chance to give those a try and really apply the definitions of left and right continuous. So question 2 asks, state whether this function in figure 15 is left or right continuous or neither at each of its points of discontinuity. So to do number 2, for starters, let's think about where the points of discontinuity are. So we have a point of discontinuity here at c equals 1, here at c equals 3, and here at c equals 5. So we'll talk about each of those points and whether they are left, right, or neither continuous. Okay. So for c equals 1, as x approaches 1 from the left, we get at f of 1, which is 2. However, when x approaches 1 from the right, we have a hole at 3, and that's not the value at 1. So I'm going to say that c of 1 is left continuous, because as we go from the left, we approach the function value, but from the right, we approach a hole. c equals 3. From the left, we approach a hole, and from the right, we approach a hole. So this is neither, okay? Because the limit exists, but the function value is down here. This is the removable discontinuity, which I think gets to another question from these problems, but we'll get to that in a second. c equals 5. From the left, I have a hole, but from the right, I have f of 5, which is 1. So we call this one right continuous, left discontinuous. Okay, question 3 asks, at which point does g of x have a removable discontinuity? Well, I just kind of gave that away. It's going to be at c equals 3, because the limit as x approaches 3 of f of x equals 4, but f of c equals, looks like about 2.5. So then the next question they ask in exercise 3 is, how do you redefine g to make it continuous? Well, you just say, okay, redefine g such that g of 3 equals 4. That basically fills in this hole, and now you have a continuous function because your limit approaches f of 3, or g of 3. They're using g for this function, excuse me. The last exercise, exercise 4. Find the point C1 at which g of x has a jump discontinuity but is left continuous. How should g of C1 be redefined to make g right continuous? Well, we have our jumps here at 5 and here at 1. So we have to ask ourselves which one was left continuous. And from exercise 2, we know that's at c equals 1. We have a jump, but it's left continuous. Now, how would we make this right continuous? Well, to make it right continuous, this becomes a hole, and we would fill in and redefine g of 1 to equal 3, because now the limit as x approaches 1 from the right equals g of 1, which we've redefined as 3. Okay, so that's just some practice with some of the definitions involving jump, removable, and one-sided discontinuity. This is kind of the first half of the video. If I were you, if you don't want to watch it all in one sitting, this might be a good time to kind of stop and then watch the second part of it. If you want to keep going in one sitting, that's fine. I'm going to record it in one sitting so we can keep going. But I know I've been throwing a lot at you, so you might need to give your brain a chance to take a break here. Okay, Now, we have one other type of discontinuity, and we've seen this one before. This is the so-called infinite discontinuity. This exists if one or both of our one-sided limits is infinite. Remember, we talked all about this. It's infinite. The limit does not exist because as you go towards one side of C, the graph goes out towards either positive infinity, as in the case of graph A, or negative infinity, as in the case of B. Now C, the graph of C brings up this parentheses here. Okay, an asymptote, you can actually have a function value at an asymptote like this. F of 2 does equal 1 here, but the limit as x approaches 2 does not exist because from the left it approaches 2, which is the function value, but from the right it goes out to positive infinity, so the right-sided limit doesn't exist. Now, what you can say, to use some of the other terminology from this section, you could call this function that's graphed here left continuous at x equals 2, but it is not strictly continuous from both sides at x equals 2. Okay, now I want to start talking about what types of functions are continuous and how we can build continuous functions off of the functions that we already know to be continuous. Okay? So one way to do this is to kind of show that a larger function is built from other functions that we know to be continuous, and the laws of continuity, which are in your book, will help you do that. And here's the big law of continuity of what it says. This can be found on page 83, the bottom of 83 on your Rogowski textbook, okay? Basically what it's saying is if you have two functions, f and g, that are continuous at this point x equals c, then their sum, their difference, their product, their quotient, as long as the denominator is not 0, are also all continuous at x equals c. Moreover, if you take a scalar constant, k, and multiply it by one of these continuous functions, you'll still form a continuous function at x equals c. Okay, that's important. That's what's basically going to enable us to take those first two functions earlier in the slideshow, the constant function, the linear function, and a few other functions that I'm going to give you in the next slide, and really prove that a lot of funky looking functions are still continuous. Okay, and there will be some exercises where you're going to do that. So what other types of functions are continuous? Now these come from theorems 2 and 3 of your textbook, which can both be found on page 84. Here's a nice little laundry list of different continuous functions. I'm not going to prove them. Your book does a good job proving them, so I would read through that to understand some of the math behind that. You're going to do some on your own, and I'll do some with you later from the exercises. But we have polynomial functions are all continuous. Rational functions within their domain are continuous. Okay, because remember we had some issues with rational functions. Sometimes there are removable discontinuities, so we have to restrict our domain to be the things that make the denominator non-zero. Okay, y equals x to the 1 over n, so basically your negative reciprocal functions, they're continuous as long as n is a natural number, and again only in its domain, because sometimes we will have some values that make this undefined. Y equals sine of x and y equals cosine of x are going to be continuous, and so too will all the other trig functions on their domains. And the book goes into some explanation of this, but I'll give you the short reason. From your trig identities, remember, the other 4 trig functions, tangent, cotangent, secant, and cosecant, can all be written in terms of sine and cosine using some of these laws of continuity. You know, for instance, tangent, think of that like sine x over cosine x, f of x over g of x. It's continuous on any point except the ones where cosine would be 0. Which is already kind of restricted when we make our domain a tangent anyway. Okay. Your exponential functions, b to the x. As long as the base is greater than 0, but not 1, you'll have a continuous function. So for instance, e to the x, because that's a base, it's a number, it's bigger than 0, that would be a continuous function on its domain. Log base b of x, again, as long as the base follows these rules, it's going to be continuous. And that would also include the natural log because the base is e. So basically, a lot of your, what I consider nice functions are going to be continuous. Your polynomials, your rationals on their domain, your trigs on their domains, your exponentials, your logarithmics, all on their domain, your reciprocal functions on their domain, okay? So what I want you to do is I want you to take a look at exercises 8 and 9. What they ask you to do is they ask you to use the laws of continuity and use some of the theorems, and by theorems 2 and 3, they mean this list, to kind of prove or show that the given functions in exercises 8 and 9 are continuous. Okay, give that a try, pause the video, and I will show you kind of what that's going to be like, because you'll have a couple in your homework too that you're going to do, so I wanted to give this to you as a model. All right, so let's look through this. So exercise 8 asks me to prove that f of x equals x sine x is continuous. So here's what I would say. First, I would say x is continuous. We know that because of earlier in the section, we know that a linear function like that is going to be continuous. We also know that sine x is continuous, and that is going to be from our list. I believe it is theorem 2. Therefore, by my laws of continuity, the product x sine x must also be continuous. Okay, so that's the kind of proof I'm looking for here. Let's look at number 9, same sort of idea. So I've got f of x equals 3x plus 4 sine x. All right, so same sort of thing. We know that x is continuous, and since that is true, 3x, that's of the form kx from my laws, is also continuous. We know by theorem 2, sine x is continuous. So 4 sine x is also. And then finally, by my laws of continuity, I've got one continuous function, a second continuous function. The sum, 3x plus 4 sine x, must be continuous. Okay? You're doing basically a proof here. You're doing a mathematical proof. You're making an argument about building continuous functions from other continuous functions and your laws of continuity. Okay, so the homework assignment that I have for you over the break will ask you to do a few more of those. Let's look at one other type of continuity problem that comes up in the homework. I want to give you practice. This is also a good type of AP question, either on a multiple choice or a free response. So they ask you to find the value of k that will make these functions continuous. So this is going back to our definition of continuity. We're basically trying to fill in the two pieces of the piecewise function to make them continuous at the given point. So we have f of x defined to be 3x plus 2 for x is greater than or equal to 1, and 2k minus x for x is less than 1. Okay, so remember what we said about continuity. The limit must exist, the function must exist, and the limit must equal to function at this point 1, as that's really the one we're concerned about, because that's where the break happens in the piecewise. Okay? So we'll start with the limit as x approaches 1 from the left. That's going to be the limit as x approaches 1 from the left of 2k minus x. Okay? Well, that's going to be, if we put in 1 for x, we get 2k minus 1. Now let's try the limit as x approaches 1 from the right. That's going to be the limit as x approaches 1 of 3x plus 2. And again, if we plug in 1, I get 3 times 1 plus 2. That's going to be 5. Now, in order for this thing to be continuous, by the way, because I have the bar at x is greater than or equal to 1, I know that this has also got to be equal to f of 1. In order for this function to be continuous, my left-sided limit and my right-sided limit have to be equal to each other. So I set 2k minus 1 equal to 5, and I solve for k. So when k is 3, this function will be continuous at 1. Let's look at the next one. Same idea. So let's try the limit as x this time approaches 2. We'll do this one from the left. That's going to be the limit as x approaches 2 from the left of kx minus 6, which is equal to 2k minus 6. Now we'll do the limit as x approaches 2 from the right. That's going to be equal to, if we put in 2 for x here, 4k. Again, I also know that that's the value of f of 2 because k equals 2. We're going to use that top function. So we need to set these two things equal to each other, the two left or one-sided limits, and we can get our function to be continuous at 2 by solving for k. And negative 3 would equal k. So that would make this function continuous. And again, you have some examples for some of these to do in the homework set. But I want to do a couple with you just so you can see how they're done. Okay, a couple other theorems that are helpful with proving continuous functions. They're up here, theorems 4 and 5. So basically, theorem 4 says if you have a function that's continuous on a certain interval, if you take its inverse, which remember, taking an inverse flips the domain and range, as we talked about in our summer assignment, that must mean that the inverse is continuous over the now new domain, which is R. Okay, which was the range of f of x. Why this theorem is useful is right here in this example, in this bullet point. This is useful because this means that the inverse trig functions are going to be continuous on their domains because of the fact that all of the trig functions are continuous on their respective domains. All right, and the last one has to do with composition of functions. So if g is continuous at a point x equals c, and f is continuous at a point x equals g of c, then the composition f of g of x has to be continuous at x equals c. Okay? We're almost done. And this is kind of the punchline of this whole section. Why do we have to go through all of this rigor in proving that a function is continuous? What does it help us with? And it's right here. It helps us make most limits a piece of cake. The point is, if a function is continuous, all we have to do to calculate its limit at a point in which it's continuous is just plug in the limit value for x. Because remember, this is the whole definition of continuity. The limit as x approaches c of f of x equals the value of the function at that point c. Therefore, if you look at these three problems as examples here, you'll notice they are all continuous functions. This one's an exponential. This one's a trig. This one is a quotient of two continuous functions, and the only place that this third function would be discontinuous is the point that would make this denominator 0, which is negative 5. And since we're not taking a limit at negative 5, we're okay here too. It's continuous at negative 1. All I have to do to get each of these limits is just plug in the value for x. The limit as x approaches 3 of e to the x plus 1 is e to the 4. The limit as x approaches pi over 2 of sine x is sine of pi over 2. And sine of pi over 2 is going to be 1. The limit as x approaches negative 1 of 3 to the x over the root x plus 5 will be 3 to the negative 1 over the square root of 4, which will be 1 over 3 times 1 over 2, 1/6. Easy. No tables necessary. You don't need to do the graphing approach that we've done before. You can just plug in that c for x. But that only works if the assumption that the function is continuous at c matters. Here's an example. The limit as x approaches 2 of the greatest integer value of x. You've all been asking me about this step function, and we've been doing some other functions. We haven't really done anything with it. Let's do something with it. So we're looking for the greatest integer value to x. So that's that step function where we start at a hole at 0, and we go across to 1 and fill that in. And then we go up and over and up and over and up, because basically this is the thing where we round up, okay? Of all of our little decimals, we round them up to the nearest integer, the greatest integer function. Well, if I look at the limit as x approaches 2, if we look at 2 here, is the function continuous? No, because the limit as x approaches the left is at 1, but from the right, it's at 2. So the limit as x approaches 2 does not exist. So I can't just plug the 2 in and say, oh, it's the greatest integer of 2, which is 2. I can't do that because it's not continuous at 2. Okay, so you have to be very careful about that. Yes, 95% of the time we can just plug a function in, plug that limiting value in. However, there is still going to be this 5% of the time when the function is not continuous at c, in which case you cannot do that. You have to either look at the graph, look at the two-sided limits, because sometimes there might be a situation where the limit is not the function value, in which case you can't plug it into the function, but you have to look at the two-sided limits, the one from the left and the one from the right. Okay, so just be a little bit cautious of that. Yes, there's a shortcut, but we don't want the shortcut to make us lazy either. Okay, with that, we have completed 2-4. Thank you for watching this video. I know it was very long. I hope you broke it up into parts and didn't watch it all in one sitting. But really get at this. Take some time. Go through some problems. Go through a few each day while we're on our break. And come back to class ready to go with any questions you have. If you have any questions in the meanwhile that are burning you over this week, please make sure to email me. I will be checking my email throughout the course of the break. Even though I will be participating in some of the events, I will still have my email with me to answer emails from time to time. All right? Enjoy the time off. Enjoy going to see the Pope. If you're going to be going down to see the Pope this coming weekend, I'll be there. Look for me amongst the crowd. And enjoy these days off. Thanks again for watching.